part of Chapter 11, we're going to discuss two things primarily. We're going to look at the equations that describe simple harmonic motion, and then we're going to go look at a second oscillating system other than the spring mass system, and that's a pendulum. But we'll start with the equations that describe simple harmonic motion. The position can be described as x equals, and let me put this x of t because this is a function of time. X as a function of time is going to equal a cosine omega t. We're starting with the assumption that x equal a at t equals 0. In other words, we're starting at a point of maximum amplitude. Cosine, of course, of 0 would be 1. So at t equals 0, we're here. Omega, if you'll remember, is that angular frequency. It's equal to 2 pi times f. Okay. I'm going to give you the other formulas, so you do not need to know calculus, but I know that some of you are already taking AP Calculus. In that case, we know that the velocity is the derivative of the position function, if the position is a function of time. So I know that the velocity can be found by taking a derivative. Okay? A and omega are both constants. But since we're taking the cosine of omega t, this will require a chain rule. The derivative of cosine is negative sine. So with our chain rule, this becomes negative omega a sine omega t, or d of t equals negative omega a sine omega t. Now, if the calculus didn't make any sense, that's fine. But really, those of you that are taking it, you know how to take a derivative of that function. That would be the derivative. If I want to get an equation for acceleration, I know that a of t is the derivative of the velocity. Again, I'm going to have to do a chain rule. The derivative of sine is cosine. This is going to be negative omega squared a cosine omega t. All right. Let's get one more relationship, and that's a relationship that says how this angular frequency omega depends on the spring constant K and the mass. We know that net force equals mass times acceleration, but for a spring mass system, this is going to be negative kx equals ma. So the acceleration at this point x equal a, t equals 0 is going to be negative ka over m. The negative is just telling you if the displacement is to the right, the force is to the left. But look here. We know that at t equals 0, x is equal to a. If I plug in t equals 0, which is going to be at x equal a, I get the acceleration must equal negative omega squared a. This has to equal this. That's a good relationship. Negative omega squared a. equals negative Ka over M. Whoops, that's a capital A. Notice the amplitude cancels out, the negative cancels out, and I get one more really important relationship, that omega is the square root of K over M. That makes sense. If I have a really stiff spring, I expect my angular frequency to be faster. I expect it to vibrate quickly. Whereas if I have a really soft spring, it may vibrate more slowly. Similarly, if I let the mass get really heavy, I expect the period to be longer. If the mass is really light, I expect the period to be shorter, which makes a higher frequency. So we've got some really good formulas here. Fortunately, you don't have to memorize them, but they're good to know. I can get a couple more relationships than what I've already gotten. I know omega equals 2 pi f. So if omega is the square root of K over M, then F must equal 1 over 2 pi, the square root of K over M. So if I want the frequency instead of the angular frequency, I have to divide by 2 pi. I also know there's a relationship between period and frequency, that those are reciprocals. If I take the reciprocal of this, then I get that the period must be 2 pi times the square root of M over K. Let's look at one example, and we'll actually have two examples. Let's do both of these examples. I think they'll both be good to do both of them. All right, I'm going to erase all my formulas. Suppose they tell us that we have an object in simple harmonic motion, and it's described by this formula. They tell us x is in centimeters and t is in seconds. Before we do anything else, we know some stuff looking at that. I know that the amplitude is 12 centimeters, and I know that the angular frequency is 0.25 hertz. Notice when you multiply hertz by seconds, you get a unitless quantity. You get radians, but radians are unitless. They want me to find the position, velocity, and the acceleration at t equals 0. Well, the position at t equals 0, of course, is just 12 centimeters. That's that amplitude. The velocity will be given by negative omega a sine omega t. So negative 0.25 times 12 sine, this will be 0.25 times 0, because remember t is 0. Well, sine 0 is 0. This whole thing will just be 0. That makes sense, because if we pull it out 12 centimeters from equilibrium, when we release it, its initial velocity is going to be 0. It will have a force on it, it will be accelerating right away, but it will start with a velocity of 0. Or if you think of a spring mass, if we pull it up from equilibrium and let it go, it's going to start with a velocity of 0. Our acceleration, negative omega squared a cosine omega t, that is going to be negative 0.25 squared times our our amplitude, which was 12 centimeters. Cosine, again, if omega is 0.25, but t is 0, cosine of 0 is 1. All of this is just going to become 1. And this came out to be negative 0.75 centimeters per second squared. So we have equations that describe it at any time. They ask us to find it t equals 0. We could have just as easily plugged in t equal 10. We'd have had some more work because we'd have had to figure out what sine of 2.5 is or cosine of however many radians. But this will give you, these equations will give you position, velocity, and acceleration for any time, not just t equals 0. All right, for the second equation, we're going to consider a spring mass system. In this case, the spring mass system is going to oscillate horizontally. It's going to be an air track glider on an air track. And we looked at this air track in a previous problem. But we've got a glider, and it's connected by a spring. They tell us K is 200 newtons per meter. The mass of the glider, 0.50 kilograms. The amplitude of the oscillation, 0.040 meters. So that's 4 centimeters. And then they ask us to find a lot of stuff. Find omega, f, t, x of t, v of t, and a of t. They want us to find the angular frequency, the period, and then they want us to find all of the equations of motion. Well, omega, square root of k over m, that's going to be 200 over 0.50. That turns out to be the square root of 400, which is 20 hertz. I'm going to write that down because I know we're going to use omega in these equations a lot. We're going to want to know that. They also want us to get the frequency. Well, we know that 2 pi f is equal to omega. So f is just omega divided by 2 pi. Comes out to be, to two significant digits, 3.2 hertz. The last one, if we want to go ahead and finish this first part, is to get the period. The period is the reciprocal of the frequency. And it comes out to be about 0.31 seconds. That makes perfect sense. This says we can do about 3 complete cycles in a second. That means the period is about 1/3 of a second. About 3 complete cycles every second, about 1/3 of a second for 1 complete cycle. I'm just rounding, but I want you to see why those numbers make sense. Okay, so now we want to go into the second part. Let's write our equations. position. In this case, that's going to be 0.040. I'm going to try to keep my two significant digits that they gave us. This is supposed to have at least 2. Cosine 20t. So for velocity, we have to do negative omega, so negative 20 times that 0.04 sine 20t. It's going to be 0.8, so negative . There we go. Acceleration, negative omega squared a cosine omega t. Now we have negative 20 squared times the 0.04, and we're back to cosine. So negative 16, that would be in centimeters per second squared, cosine 20 t. So we can do a really good job of describing the motion at any given time using these. If they said find position, velocity, and acceleration at t equal 3, I would just plug in 3. 0.040 cosine 60. Okay, let's talk about pendulums. We're looking at what's called a simple pendulum. A simple pendulum is a mass at the end of a string that is, quote, weightless, or more practically, a negligible mass. It's very light compared to the mass. There is such a thing as a physical pendulum, like you might have a solid bar that's suspended by one end and swings back and forth, in which case it's not a simple pendulum, because the center of mass is not at the very end, but located somewhere in the middle. But we're looking at just this very simple one. So you have, we'll hang it from here. And you pull it over to the side, you raise it up. And when you let it go, it's going to swing, as most of you know, back and forth. It won't go any higher than what you launched it, because it gains a certain amount of gravitational potential energy. And when it swings back, it's got to have the exact same amount of gravitational potential energy. Try to make it look a little more symmetric. Okay, pretend that's a perfectly symmetric picture. I know it is not. Okay, so what provides the restoring force? Well, actually, it's gravity, because even though it's not a lot higher, you can see when you pull it over there, it gains some gravitational potential energy. We know that gravity hangs straight down. Let's extend this line. There's theta. Some portion of the gravity, if we make our XY axis look like this, the part of gravity that is along this line, theta is the maximum, we call that That's the angular displacement or the amplitude. How far did we pull it over? Okay, you can see that the portion of the gravity that is along this line, I'll call that a vertical, is just mg cosine theta. Mg cosine theta has to balance out that tension. There's also a part that points perpendicular to that wants to make it swing down. That's mg sine theta. And this is the restoring force. So when you hold this up here, the part that make it swing sideways is this restoring force. It wants to go back to equilibrium. Well, think about it. When you let go, it has all potential energy, no kinetic energy. When it reaches equilibrium, it no longer has, if we consider this a height of 0, it no longer has the gravitational potential energy that it gained, but it's all kinetic, so it won't stop. It will keep right on going until all of that kinetic is back into gravitational potential energy on the other side. So here's our situation. F equals mg sine theta. Now, what you may, and actually technically it's going to be negative because it's going in that negative direction. What you may not know is that if we're working in radians, and we are going to be working in radians, is that sine theta is approximately theta for small angles. And we go, well, that's craziness, Hughes. That can't possibly be right. Well, let's do some looking. Well, what's a small angle? We've got to be in radians. 10 degrees, that's a small angle. 10 degrees is what? What's pi over 12? Pi over, let's think about this. Pi equals 180 degrees. So 10 degrees is like pi over 18. We could start with 5 degrees if you wanted to, but that's fine. 10 degrees, about pi over 18. So if theta is pi over 18, well, I want to get this as a decimal. Get my calculator. Let me make sure I'm in radian mode. Okay, I'm in radian mode. Pi over 18 is like 0.1 74. Well, let's see what sine of pi over 18 is. Sine of pi over 18. It's 0.174. That's kind of strange. The first time I learned that, I was like, really? If the angle's small and we're working in radians, theta and sine theta are probably pretty much equal. Let's go a little bigger. So let's do 20 degrees, twice as big. 20 degrees is pi over 9. Okay, well, let's do pi over 9. Pi divided by 9, it's like 0.349. Let's do sine of pi over 9. not quite as accurate. It's about 0.342. So not exactly equal, but that's still pretty good, 0.349, 0.342. Anytime you're at 20 degrees or less, they're virtually the same. Let's go up to 30 degrees. So 30 degrees is pi over 6. That's 0.524 sine of pi over 6 is 0.500. So a little farther off. As we get the angle that's larger and larger, it's going to get farther off. But if we talk about small angles, think about pendulums. You don't pull a pendulum way up here to 90 degrees. You generally pull a pendulum out probably 30 degrees. Maybe people get crazy and do it for 40 degrees. I mean, 40 degrees would be what? 2 pi over 9 would be twice as big. If I do 2 pi over 9, that's 40 degrees. That's 0.698. That's as big as I'm even going to consider, because that's really not a small angle anymore. Sine, and that's 0.643. So we're getting farther off now, clearly. But I just wanted you to see, when you talk about small angles, 10 degrees or less, theta equals sine theta. Even if you're 20 degrees or less, theta is really close to sine theta. Heck, all the way up to 40 degrees, it's not crazy far off, but it's a little far off. All right, so what's the point in all of that? Oh, and I want to tell you the length of this string is L, because we're going to need that in a minute. That means F, the restoring force F, is about mg theta. I know that, where's my, if I want to consider this distance x from here to here, remember that's an arc length. The arc length in radians is simply equal to L theta. It's equal to the radius times the angle, which means theta equals x over L. Now, why did I go to all this trouble? I went to all this trouble because mg and L are all 3 constants. So, simple harmonic motion is described as any motion where the restoring force, this is the restoring force, is directly proportional to the displacement. X is the displacement. We've shown that for small angles, probably 30 degrees, 25 degrees or smaller, that pendulum motion very, very closely approximates simple harmonic motion. It's not perfect because the restoring force isn't truly directly proportional, but it's almost. We made this one jump saying, hey, sine theta is about theta, but I know that the relationship between x, L, and theta is this. So if I put that in there, I can see that the force is more or less proportional to the displacement. That's a whole lot of work. But I just really wanted to show you that. What that means is, for a pendulum, our spring constant isn't a spring constant, it's mg over L. And so omega, which was the square root of K over M, becomes the square root of mg over Lm. Those m's are going to cancel out, and we get a relationship that says for a pendulum, the angular frequency is the square root of g over L. So the frequency of a pendulum does not depend on the size of its mass at all. A heavy pendulum can have the exact same period as a small pendulum. It depends on the acceleration due to gravity. If you're here on Earth, that's going to be 9.8, and the length of the pendulum. As you let L get very, very large, you get a very long pendulum. The angular frequency is going to be much smaller. You're going to get a low frequency and a long period to go with it. Similarly, that means that the frequency is 1 over 2 pi square root g over L. If I take that reciprocal, the period is 2 pi square root of L over g. Fun fact, the square root of g is almost equal to pi, so a lot of times here on Earth, people will use an approximation that the period is just 2 times the square root of the length. I can show you that too. If I do the square root, I know that pi is 3.14. The square root of g, is 3.13. Now, that's only a good approximation on Earth. If you go to the moon or you go someplace where g is not 9.80, you can't say. But here on Earth, only on Earth, the period is pretty much 2 times the square root of L. So that's a nice quick way of calculating the period of a pendulum if you happen to be right here on good old planet Earth. Regardless of where you are, however, we see that the period depends only on the length of the string and the gravitational constant. All right, let's look at an example. You'll probably never have to recreate any of this, but it's important for me that you see where I get it from. It says, what is the period of a pendulum that has a length L that is 1 meter exactly, there, not exactly, in Pittsburgh, where G is 9.801 meters per second squared. Obviously, if we're going to get this right to 4 significant digits, we're not taking any approximation shortcuts. The period is 2 pi square root L over G. I'll plug in my numbers. And I get a period that is 2.007 seconds. If I want to know the frequency, I take the reciprocal. It's going to be very close to 1/2 because the period is very close to 2 seconds. Comes out to be 0.4983 hertz. Okay, another pendulum example. One of my favorites. And I think it's my favorite only because it always makes me think of the little Martian on Bugs Bunny. It says an easily lost Martian carries a ball on a string to use as a pendulum. On Mars, and the gravity on Mars is 0.38 times the gravity on Earth. On Mars, the period is 1.5 seconds. He's on a strange planet. And it has a period of 0.92 seconds. Where is he? How can we find? He obviously carries around a list of gravitational constants or something. I would approach this and say, well, you know what? Let's find how long my pendulum is. How long is this ball on a string? I know the period is 2 pi square root G over L. Make sure I flipped everything upside down to get that right. Nope. L over G. That's correct. So if I want to solve this first situation on Mars to see how long his is, I need to square both sides. I'm going to get T squared equals 4 pi squared L over G. Notice how that works. When I square a square root, I just get L over G. But when I square T, I get T squared. When I square 2 pi, I get 4 pi squared. I know everything but L. So I'm going to have 1.5 seconds squared times G. Well, G for, well, I'll tell you what, let's finish solving this and then we'll plug it in. I want L. L is going to be T squared G over 4 pi squared. Just cross multiply that if you need to get that straight. How did she solve that for L? It's T squared G over 4 pi squared. So 1.5 squared. If I'm on Mars, it's 0.38 times 9.8 over 4 pi squared. So I can solve for the length of his string. 1.5 squared times 0.38 times 9.8 divided by 4 divided by pi squared. And the length came out to be 0.2122 meters. If they had asked how long the string is, I would have answered to right here. I only had 2 significant digits, but I'm going to use this in the next thing. So our next problem, I want to try to figure out what planet I'm on. Like I said, I think he must carry a table of gravitational constants with him. I'm going to solve for G. If I take this formula and I solve for G, this one right here, G is equal to 4 pi squared L over T squared. So he's on the new planet. We know that the length of his pendulum that he carries around, the period on this new planet was 0.92. Let's see if we can solve for what the gravitational constant is. Four pi squared times 0.2122 divided by 0.92 squared. Oh my goodness. Came out to be 9.89 meters per second squared. Where is he? Well, if he's in our solar system, he's on Earth. Only place in our solar system that has a gravitational constant that's of 9.80, but does vary. Maybe he's down in the very depths of Death Valley or some other very low place. Makes the gravity a little bit stronger. If I hadn't carried this, I might have gotten closer to what the book expected and try it without it just to see. Just to see. They may not have expected me to carry that extra with me. Just do a second enter, take those 2's off, see how much difference it made. If I hadn't, when I take that little bit of extra, it comes out to be 9.79. So yes, definitely landed here on Earth. All right, that takes care of pendulums. Everything in nature vibrates at something that we call its natural frequency. The natural frequency for a pendulum is the square root of G over L. Actually, it's 1 over 2 pi times the square root of G over L. But everything has a natural frequency. However, we can do things to change that system. We're going to look at that. In real world systems, they have friction and things will die off, the amplitude. So in a real world, this is what we expect to happen. If we start with a fairly large amplitude and a fairly regular period, we may maintain the period, but you'll notice that's what most like grandfather clocks, they'll keep that period pretty constant, but the amplitude gradually dies down. If you want to, and sometimes that's deliberate, sometimes you want it to die down, like shock absorbers in a car. When you have this deliberately dying down, we call that damping. And damping can be quite deliberate, like in shock absorbers. If any of you have ever studied piano, there's a pedal that's sometimes called the sustain pedal, but sometimes you hear it called the damper. The way the piano is set up, the keys are naturally damped, so that if you hit a C, it just goes blink, blink. But if you want that sound to continue to vibrate and you press on that sustain pedal, also known as the damper pedal, it lifts the damper up off the strings. And then instead of hearing just a little blink, you hear blink. It'll just carry that sound through longer, okay? So damping is where you lose amplitude. If you don't want to lose amplitude, you can fix this by giving it a little push at just the right time. Here, and here, and here. This periodic force is called a driving force. And by giving that a little extra force, you can get it to go back up to where it was. And it'll do better. And then you go, oh, nope. And you won't be losing that amplitude. That driving force will help you keep that amplitude. Okay. Grandfather clocks use weights in there with some pulleys to help provide that driving force so that it doesn't just, when you start it swinging rapidly, die off. Now, if you've ever been on a playground and you had your parents push you, they provided the driving force. If they provide just the right amount of force, they can get you going as high as you're comfortable with, and by giving you that little extra push each time, they keep you swinging. Now, you can even have what we call a forced oscillation. In a forced oscillation, rather than let something swing at its natural frequency, picture a kid on a swing. And the natural frequency is doing this. And they are big kids, so they know how to pump their legs. Remember how you learned how to kick out and pump your legs? And you could maintain. But what if there's a couple of bullies? They don't let you go. They come and get behind you, and instead of letting you swing out to your natural spot, they come in right here and they push you. So you swing back. But here's another bully, and he pushes you. So instead of swinging back at the natural frequency, it's like bam, 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 bam. That's a forced oscillation. Okay? A forced oscillation is not applied at the natural period. Like this driving force where your parents are just gently pushing you. It tries to change the natural frequency to a different frequency. Okay? Now, the other idea that we want to talk about while we're talking about driving forces is something called resonance. Now, what happens if somebody applies this driving force, but it's not just enough to maintain? What if you're really little and you don't know how to swim? Your parents, each time they push you harder, you can get a situation where you start with a fairly small oscillation, but they keep pushing you at your natural frequency, and you can get really large increases in amplitude. That happens when your driving force is at the natural frequency, but it's larger than what you need to just overcome friction. Usually you want a driving force maybe to just overcome friction so that you just continue to oscillate at a certain amplitude at the natural frequency. With resonance, you're still vibrating at the natural frequency, but the force that's pushing you, the driving force, is too large or deliberately large. So you keep getting higher and higher oscillations. One example of this, how many of you have ever seen a commercial? These were some old Memorex commercials, and you can Google it on YouTube, where Ella Fitzgerald would sing, and the pitch of her voice vibrated the wine glass at its natural frequency. We all know, we've seen it with water and played with our fingers, that a wine glass has a natural frequency. It creates a pitch. Well, if she sings, and she's deceased now, but this really big voice, she would cause that wine glass to vibrate at its natural frequency, and it would vibrate so fast, eventually it would shatter the wine glass. All right. It even can happen with things you wouldn't think it could happen with. If you want to be entertained, Google the Tacoma Narrows Bridge. On YouTube. The Tacoma Narrows Bridge was a brand new bridge. I forget what year it was built. It was just a few months old. We're talking about steel cables and concrete, and the wind started to blow. And the wind blew at its natural frequency just enough that it started oscillating. And it oscillated bigger and bigger and bigger until that bridge was shattered. So, Tacoma Narrows Bridge if you want to be entertained. That is the end of chapter 11, and I will see you in chapter 12.